So the Fourier transform of j 2 pi f the Fourier transform of this x of t is this one. This is by using differentiation property. So it is equal to 2. Therefore x of f is equal to 2 by j 2 pi f, which is equal to 1 by j omega. So it is equal to 1 by j pi f. So we can write the Fourier transform of this HGN or the signum function is 1 by j pi f or 2 by j omega. So this is the answer. The problem was asked for the 6 marks in exam. Next problem. Obtain the Fourier transform of rectangular pulse so x of t is equal to a rectangle of t by capital T, and sketch its spectrum. So the rectangular pulse of amplitude a and width t we will draw here. It is x of t, this function, that is a rectangular of t by t. So according to the definition of Fourier transform, we write here according to definition of Fourier transform, x of f is equal to minus infinity to infinity x of t e raised to minus j 2 pi f t dt. Now here x of t is a and it is from minus t by t to plus t by t plus t by 2. So we can write So we can write here x of f is equal to minus t by 2 to plus t by 2 a into e raised to minus j 2 pi f t dt. So because here value goes from minus t by 2 to plus t by 2, so this is the value of integration. So it becomes a by minus j 2 pi f so we substitute these integration values here. It is t by 2 and minus t by 2. So by solving we get the answer as e raised to j pi t. This is equation number 1. Now according to Euler's identity, what is sin theta? Sin theta is e raised to j theta minus e raised to minus j theta by 2j. So we write here according to Euler's identity, what is that? Sin theta equal to e raised to j theta minus e raised to minus j theta by 2j. Now here what is theta? Here theta is j pi f capital T. So equation becomes x of f is equal to a by pi f into sine of pi f t. This is theta. This is equation number 2. Now we have to multiply and divide by t to above equation. We write here multiply and divide by t. So equation becomes f of x of t is equal to a t sine pi f t divided by pi f t. This is equation 3. Now in equation 3 we can write this 3 equation as in equation 3 sine of pi f t divided by pi f t is equal to sin of f of t. So we replace this above equation as x of f is equal to a t sin f t. So this is the Fourier value or Fourier transform of rectangular poles. Now we have to draw the amplitude spectrum for this. Now we draw the amplitude spectrum for this sinc function. So it becomes this is 0, this is minus 1 by t plus 1 by t, it is minus 2 by t, this is plus 2 by t, this is minus 3 by t, it is plus 3 by t. It is x of f magnitude. This function is a t. It is amplitude spectrum. So this is amplitude spectrum. Now we have sinc 0. We have sinc 0 is 1. So 80 sinc 0 is 80. Okay. Now the sinc function will have a 0 value for the following values of f of t, such as sinc of ft is 0 for ft is equal to plus minus 1 2 plus minus 3 dot dot dot. That is for f is equal to plus minus 1 by t plus minus 2 by t and plus minus 3 by t dot dot dot. So the phase spectrum has been shown here and it has a 0 value for all the values of f. So this problem was asked in exam for 4 marks. Next is state and prove linearity property. So it is also called as superposition theorem. Now the statement for this is consider two signals x1t and x2t having Fourier transform x1 of f and x2 of f. So consider a1 and a2 are arbitrary constant. Then we can write a1 x1 of t plus a2 x2 of t and its Fourier transform a1 x1 of f plus a2 x2 of f. So we have to prove this. Now proof for this. Now according to the definition of Fourier transform, according to the definition of Fourier transform, we can write f t x of t xf minus infinity to infinity x of t e raised to minus j 2 pi t dt. Therefore, f of t is a1 x1 of t plus a2 x2 of t. We can write minus infinity to infinity a1 x1 of t plus a2 x2 of t into e raised to minus j2 pi f t dt. So we can write a1 into minus infinity to infinity x1 of t e raised to minus j2 pi f t dt plus a2 into minus infinity to infinity x2 of t e raised to minus j2 pi f t dt. So by comparing each integration term, we get Fourier transform of a1 x1 of t plus a2 x2 of t equal to a1 x1 of f plus a2 x2 of f. Now from we can it is a1. Now we can say it is a2. If we calculate the Fourier transform of individual term and add the result, then it is same as calculating Fourier transform of addition of signals. This property is useful to calculate the Fourier transform of waveform, and it is divided into addition many simple signals. Then Fourier transform of each signal is calculated separately and result is added. So in this way we will see the next properties, few more properties in the next lecture.